Yes, thank you so much for coming another time. Last time we had a problem we were able to resolve by completing the table of values as was given to us on the table that day on the board. But because we had issue, we don't have graph on the smart graph on the board. We decided that we are going to continue by solving that thing graphically with the materials available. So today we will draw the graph. Let me recall to you those questions we had last time. After completing the table last time, we asked some questions. You see, from the completed table, plot a graph of function of time, that is charge as a function of time versus time, and deduce the slope. The second question says determine the time when the capacitor is fully charged from the graph. And the third question says discuss the graph. So now let me recall to you the completed table. Read it boldly so that those of you who are not able to see it clearly will at least know what the values are. So the time in seconds is a serial number. This column is for time in seconds, that the time as we were able to compute. So the first values here is 0.0004 seconds, and then the value here, second value 85.0000, third value is 175.0000, fourth value is 340.000, fifth value is 425.000, the sixth value is 440.0000. So for the voltage in the system that is measured in volts, what we had that day was a constant 12 volts, 12.000 all through. And then for the voltage across the capacitor, we said we had the value 0.000 at initial point when that time was still 0. And then we had 7.560000. We had 10.56000, 11.78000, 11.88000, 11.93000. Then for the current in ampere across the resistor, we had 0.00. And there's something we said that day. The current across the resistor in ampere is still the same thing, equivalent to the current in the capacitor, also in ampere, because current is measured in ampere. So the values include 0.00024, 0.00008, 0.00003, 0.00004, 0.00002, 0.00 as time proceeds. Then for the function of time, the charge as a function of time that is measured in coulombs, we had 0.000 at the initial, that is when time is 0, 0.01260, 0.0174, 0.01960, 0.01980, 0.01990. So now that we have read the values, I have also made effort to plot the graph. So, but for those of you who cannot plot graph from the beginning, I will show you exactly what I have done here. Look at it very clearly. You see, what I did, I put the title of the graph, a graph of a function, the charge function as of a time versus time, and then I drew my vertical axis, taking the axis from origin 0, and this one is going to the time. This is representing the ordinate, and this is representing the abscissa. So this time is in seconds. I took the scale and I told myself that the scale for the function of time, that is charge, should be 2 centimeters to represent 0.002 on this charge function, that this charge axis, that is on the vertical axis or the abscissa, or what we call the ordinate. So now for this side, which is the ordinate, the abscissa, we say time. This is the x-axis. So we are representing 50 on, that is 2 centimeter to represent 50 units on that axis. Based on that, we have seen that the readings we started our reading from 0.02, that is 0.002 to 0.004, each 2 centimeter as we proceed along that axis. And then in this axis, we had 50, 100, 150, 200, 250, 300, 350, 400, 450, and so on. And now, we have seen that during the deduction, when the time is 0, the charge is 0. And that is this particular point that was marked here. You see that at that origin. And then when the time is 85, 85 is somewhere around here, because this is 50. So each of these boxes representing 5. So this is 55, 56, 56, 65, 70, 75. So you see that point that is traced to 85 here. And that value at that 85 is 0.0126. And that is what is marked here. So it has been plotted. And then we move again to 175, which is this is 150. So 175 is here. And you can see that we have traced it to mark that particular value where it is 0.0174. And that has been traced here. Okay, so this is the same way we did this when this one was this particular 340. This is 300. So 340 should be around here. And that has been marked and plotted. Okay, so we did this continuously till we finish plotting the whole values against each other. And now we joined with a ruler with a curve. Take your maybe a piece of broom and join this curve because it's not straight. So if you join the whole point, you have this particular curve here. You see the way it is going exponentially. It is going this way. So now I took a tangent at this particular point and then made my right angle triangle. Now that I've made my right angle triangle, I can now deduce the slope. So for the slope, you can now see when you take it, if you turn this particular graph, you see that the slope is a change in the Q all over change in time. And that change in the Q, what did I do? You can see the tip of this right angle triangle, the highest value, because it is positive. So the positive slope means it is moving from the hypotenuse is facing this side. Because the hypotenuse is facing this side, I'm going to take this to be the highest point of QT. And that is, if I take this reading, you will have that particular value that is shown here. That is 0.02. Okay, so this 0.02 subtracted, if you subtract, I think I'm having a kind of a miscalculation here. This is 0.02. If you check it to the other side, if you multiply it if you multiply each of these things is representing 0.0001. So by the time you take the difference and then divide by the difference you have here, that is 300 minus 50, you'll be having 300 minus 55, because that particular point where this thing strike is 350. 300 and yeah, that is 305. So if you do the subtraction very well, you will have 305 minus 55. Sorry, 300 minus 55, this particular 55. So, and that is what gave us 0.07 divided by 245. So if you do this division, you will have 2.8571 times 10 raised to the power minus 5 ampere. And that is the slope. So to answer the second question, which says determine from the graph, determine the time when the capacitor is fully charged from the graph. Now, let us look at the graph, the curve very well. If you look at this curve very well, you can see it started from the origin 0 and moves exponentially. Look at this point where it becomes very big. And then how do you you recall that what we solved that day, we said Q naught, the Q0 is 0.02. That is what we have solved before in Coulomb. So if you take that 0.02 from this charge axis, you will realize that if you trace it, it will touch this curve at a particular point here. Now trace that time down. If you trace that time down, you get it exactly at 455. So that is 455 seconds is when the capacitor is fully charged. Okay, so that is in seconds. And then the third question say discuss the graph. For this discussion, you can discuss it in the way you wish, but basically what you should know is that it is an exponential function. As from the origin, the graph started rising to a point where it begin to slope. That time it begin to have maybe a much less streamline or steep here. At this particular, that is when there is no more current to push, because the current is tending to zero. No current started from somewhere, a particular value, and is going down. So because it's not driving again, you see the difference even in the values are not much farther again from each other. And again, it begin to go down, though it may not go to zero, because it continue to, it's an exponential function. So because of that, these are the things you should speak about the discussion of the graph. So one is that it is an exponential. Two, that at a particular point, from maybe at this particular point now, the value started being close, irrespective of how far the time is going. They started, because the amount of current in that system is going down, and because it's going down, it needs a support to push this thing further. That is why the values begin to close in. Okay, so now there's something we will do. I did this effort here because I may need to use the Excel system in my personal computer, in my PC. But because some people may be saying, how do we plot this thing on a graph paper? That's why I went to conventional, the old method. So next time I'm going to use the computer. I'm going to plot this thing using the Excel function, or SPSS. So when I do that, I will still display it for you to see that it is possible for you to plot. If you don't have that, you can still deduce your functions in capacitor with this. So what is the essence of this? The essence of this is for people to have in-depth knowledge, so that by the time we start designing our capacitor with those equations that I want you to get familiar with, you will be able to know exactly what you are doing at any point in time. Thank you so much.